We are now to actually defining the math that goes into these things. So hopefully all of the terminology makes sense, and then we don't have that much to do in the way of math. So keep in mind that again, we're always talking about displacement in terms of two variables. Let's start by looking at a snapshot graph, which means we're looking at one moment in time. So this one moment of time comes over here, and notice that our function is then not of time. So that means we're going to have to think about that later. But we have a sinusoidal plot of position. Our wavelength is lambda, and so lambda is determining the periodicity of this. Phi is our phase constant, and this was something that also showed up in terms of the pendulum. So notice that this is expressed as a sine wave, and so sine waves should be starting there, or if we continue this curve backwards a little bit, we would think about a sine wave starting at a displacement of 0 at x equals 0. So the fact that it is shifted a little bit has to do with that phase constant. So figuring out the phase constant can be a little bit tricky mathematically, but it just allows us to have any sort of starting condition we want along the sine wave. So that's all. So now if we want to introduce time, we can think about position transforming from just x, whatever our position is, to a new position, which is now x minus v times t. So v is the wave speed and t is, well, time. And so what we're doing is saying, well, at some later time, we've taken this and we've moved it some amount over where that is just some delta x, and delta x equals v times t. So we can kind of take this new one, and I'm going to do my best to draw it, and we have a new sine wave. Nope, I'm going to do a terrible job drawing it. We have a new sine wave. And so at a later time, we are actually seeing the wave that had been over to the left. So the reason it's a subtraction is that the displacement was effectively what we had earlier to the left. So don't worry too much about the derivation of this, but that's where it comes from. So again, we can say that we've shifted it a little bit, and we can then put in that v times t. Notice that now this is truly a function of t, so this is our displacement now as a function of position and time. This is not the form we normally see it in. We need to do a little bit of rearranging. The book goes through it in detail, but I'm going to skip a couple of steps here. Effectively, we're going to introduce some new variables that leads to some symmetry in how we express this in terms of position and time. So let's talk about that. We're going to have a quantity which we'll call angular frequency. This should look familiar. We saw this when we talked about circular motion. We saw this when we talked about pendulum. So this is 2 pi times our normal frequency. So do be careful when you say frequency, whether you mean, well, normal f frequency or angular frequency. And so since f is 1 over period, 1 over t, we can express angular frequency as 2 pi over t. A new value that might not be familiar to you is wave number. And you can see that while angular frequency was 2 pi over period, wave number is 2 pi over wavelength. So there's kind of this symmetry here between these, and that's going to be something we use in the math. Now notice that this is k. What other k's values have we met in physics in intro, either semester? Well, k has represented a spring constant. K has represented, what else? Other things, right? There's like Boltzmann constant. There are other constants that we've talked about as well. So be careful because k is a value we've seen before, and now it's, maybe it was kinetic energy, and now it's also wave number. So be careful in your notation. Again, recognize that k shows up in different ways on the equation sheet. So we're going to introduce this. We have this nice symmetry. We can now write, after a little bit of math, again, you can see the book for the details on this, as we have our function of position, k times x. Now we have our function of time. Notice it's minus omega t, where this is related now effectively to velocity. And again, we've kind of actually lost velocity here. We've removed it, and that had to do with what was appearing in our previous equation. And we still have good old phi, our phase constant here. So this is a nice way to write this. This is the best way to think about it, but you have to know that k here is our wave number, omega is our angular frequency. So there's a lot of other values that you might need to use to actually get to these, but this is the simplest way we typically write this. So if we then return to our plots to now try to connect what our representation looks like compared to our math, if we have a history graph, that means that we're looking at a function of time for one position in space. So we have to take our two-dimensional function, we plug that in here, but now we have a function of this. So notice that this is a constant and this is a constant. So this is effectively saying that I have a sine of negative omega t plus some new angle, I'll just call theta, some new phase. Sorry, it's not truly a physical angle, it's a phase. That's a combination of these two. So again, it's still sinusoidal with some phase, and that's what we see up here. So similarly, we can then look at our snapshot, which is at a specific point in time, and we then have a plot of position. So again, we have a constant here and we have a constant here, so you can imagine rewriting this as kx, and then I can just call this, I'll call it an alpha, which is effectively this new phase. So again, you have a sinusoidal function of position with some phase involved. So again, you have this repetition here. So hopefully that's clear. Again, when we're doing that plot, we're really only just showing one variable at a time, but we do at least have a way now of writing this function of displacement in terms of both variables at once.